All right, we're ready for lesson 0.8, and today we're going to break this up into two different parts. But part one, we're going to be looking at simplifying radical expressions, and I'm going to show you two methods, and you pick the one that you like the best. To start with, though, our first problem in this example says the square root of 25, and I don't want to assume that we all understand what this means, so I'm just going to go back to the very beginning, maybe when you first were introduced to this whole idea of radicals. This is a square root, and for square roots, there's always an invisible. You don't see it, but there's an invisible 2 there. It's called the index. And what that 2 represents is we're trying to find the number that when multiplied by itself, the same number, I'm just calling it x right here, the same number multiplied by itself would equal the number underneath the radical. That's called the radicand. Well, in this case, this is the square root of 25. We probably know what this would be. That number would be 5. The same number that when multiplied by itself equals 25 is 5. Now, notice I'm going to write something incorrectly on purpose, but I see this quite a bit. The square root of 25 is the square root of 5. Well, it's not the square root of 5. We're just looking for the regular non-radical number that when multiplied times itself, 2 times, equals the number underneath. So if you're in the habit of saying the square root of a perfect square number is another square root, that's not true. So we'll try to break that habit. Now, number 2 is a different story because there is no number that I can multiply by itself to equal 45. So this is not a perfect square root number. So there are two methods we're going to look at in simplifying these where we don't have a perfect square root number underneath the radical. And the first method I'm going to show is really prime factorization. I'm going to come up using prime numbers, and the prime numbers start with 2. Prime numbers have 2 factors. 1 is always a factor, and then the number itself. And the number 1 is not prime because those 2 factors have to be different. Okay, so 2, the number 2 is the first prime number. 3 is the next prime number. 5 would be the next. 7, 11. Somebody tell me what the next one would be after 11. 13 after that. 17. Next one before that. 19. 21 has 1, 3, 7, and 21. So 21 is not prime because it's got 4 factors. So only 2 factors, 1 and the number itself. So in writing 45 using what we call prime factorization, only prime numbers, this would be how I write 45. Now, you could also go back to your past when you learned how to do factor trees. Y'all remember this? Breaking a number up into prime factors. Who remembers this from your past? I see just a few hands. Okay, I thought this would be something that a lot of people would learn. But this is a way you could come up with those prime factors. A lot of these numbers, you should be able to get there pretty easily. So using this prime factorization method, since there is you can always remember it this way, since there's a 2 here, we're looking for pairs. Okay, the number 2 is a reminder. I'm looking for prime factors that appear in pairs. Well, I have a pair of 3's, so that means I'm going to write the number 3 without a radical to represent the fact that I had a pair of 3's. I do not have a pair of 5's, so 5 is going to stay under the radical. So this ends up being what we call the simplified radical form. So you break up the number into prime factors, and then you start looking for pairs. And every time you have a pair of prime factors, you get to bring that number out. The goal of this game is to see, let's see how much of this number 45 we can get out from underneath the radical. And we got pretty much a pretty good chunk of it. The only thing that was left that had to stay was the number 5. Okay. Now here's another method. not, again, I'm not saying you have to show both, but some of you will like this better because when these numbers get a little bit bigger, you're going to be doing a lot of factoring, and that's okay if it means getting it right. But if you know your numbers that are perfect square root numbers, you can go ahead and factor like this. I use 9 because it has a perfect square root and it also divides into 45. So these two radicals multiplied together equal the original problem. And now it's just a matter of simplifying the square root of 9. And I got exactly the same answer, but to me, since, well, I'm pretty familiar with the perfect square root numbers, I like this. I think it's quicker, it's easier, but some of you will use this and it's fine, no problem. I want to show you both, and then you just pick whichever one you like. Okay, number 3, using prime factorization. This would be the prime factorization of 27. Now I'm looking for pairs of 3's. I see a pair of 3's, so that means my answer will contain a regular 3 to represent the pair that comes out. And then this 3 doesn't have a pair to go with it or another 3 to go with it, so it stays under the radical. There's my answer. Using this same method as I did before, I would just do the square root of 9. Square root of 9 times the square root of 3. Because those multiplied together. So you're always looking for a perfect square root radical multiplied times a non-perfect square root, and then simplify the perfect square. So same answer, different method. All right, let's talk about number 4. I'm going to erase this to give myself a little bit more room. So let's use the prime factorization method. So if you used factor trees, maybe you started with 8 times 10. This is really just for people that might not understand how to get to prime factors. So I just circled all the prime factors. So I got 4 2's and a 5. All those numbers multiplied together should equal 80. Now I'm looking for pairs. So I got a pair of 2's. All right, I'm going to write down 2. Got another pair of 2's. I'm going to write down another 2, and I'm going to multiply those together. Go how many numbers come out of the radical, they get multiplied together. 5 did not have anything to go with it, so 5 is going to stay, and so my final answer is going to be 4 times the square root of 5. If you used perfect square root factors, you could do the square root of 16, which has a perfect square root, times the square root of 5. Those 16 times 5 equals 80. And then you just have to simplify the square root of 16. And you're there. It's just, to me, it's a little bit quicker. Okay, any questions about either method? How many of you seen in the past the prime factorization method? You've seen that before? 1, 2, 3, 4, 5, 6, 7, 8. Okay. What about the other method? Have you used this before, where you just you do factoring using a perfect square root? Okay, I see a couple hands. All right, good. Do you have any questions so far? Any questions? No? All right, now let's throw some variables in the mix, and let's see how we treat variables. So we'll go ahead and do the prime factorization of 20, just like we did before. Two times 2 times 5 equals 20. This would be 3 x's, 5 y's, and 6 z's. So literally, if you had to do this and you're doing prime factorization, this is what it would look like. And now we're looking for pairs of numbers and variables. So I got a pair of 2's. So 2 comes out. and 5 is going to stay under the radical. I got a pair of x's, one x comes out, and then this x is going to stay. All right, I got a pair of y's, y comes out. I got another pair of y's. Well, this would become y to the second. It's like I had two pairs. Well, I don't have another y for this, so y squared comes out, and then y is going to stay under. Do you see how I got y squared? Okay, let's talk about the z's. I got one pair of z. I got two pairs of z's. That would make z squared. And now I have three pairs of z's. That makes z cubed. So every time you have a pair, that just raises the exponent that many times. All right, so we have what came out, and now what stays under? The 5, x, and y. Okay, questions? I'm going to let you try number 6 on your own, and we'll see how you do with it. You didn't have to do this, but what I did over here to the right for number 6 is I used that alternative method. And let me just explain it. You might like this better. I think it's quicker. But I did the square root of 9 times the square root of 2 to make 18, and I used 9 because it has a perfect square root. When it comes to variables, variables have perfect square roots if their exponent can be divided by 2. So the way I simplify the square root of a to the 4th, it's really like saying a to the 4 divided by 2 power. And b also 4 divided by 2 power, and c would be to the 6 divided by 2 power. So if you like that, it's quicker, it's easier. Once you get used to it, it saves you a little bit of time from having to list out a bunch of factors. But here's the bottom line. Let me see who got this. So you got 3a squared b squared c cubed times the square root of 2ac. Who got that right? Right. Does anybody have a question? I'm going to have you try number 7 now. Try number 7. So using prime factorization to make 8 times 7 is 56. So this would be 2 times 2 times 2 times 7. That's the 56. I got 2 A's, 4 B's, and 5 C's. Now we look for pairs. So I got a pair of 2's. So 2 comes out. 14 stays. There's no other 2, no other 7. So 14 is going to stay under. I got a pair of A's. So A comes out. I got 2 pairs of B's. So B squared comes out. I've got 2 pairs of C's that can come out, but then I've got a C that doesn't have another C to go with it to make a pair, stays under. So this is out, and then everything else, 2 times 7 times C, stays in. What I did over here is just I did the perfect square. If you like it, make a perfect square root. Variables that have perfect squares have exponents that are divisible by 2. They're even numbers, in other words. kind of like that better. I don't guess anybody in honors geometry. This is what I do in honors geometry, but I don't think anybody's. Okay. Um, that's it. That's as far as we're going to go today. So let me have you turn to the practice page, and I'm going to modify the assignment just a bit.